So we're happy to have Professor Liran Goren from Goren University. Liran is working most of the time on surface dynamics, surface process dynamics at various time scales, and that's it, I guess.
Thank you. Thanks. Hi, everyone. Congratulations, Alona, and thanks for the invitation to speak in front of you today. Any chance the air condition can work harder?
No, we don't want that. It's going to get cold in a minute. It's going to get too cold.
I hope it's going to get too cold. Okay.
It's directly on you, so if it's too much.
It's not. Okay. So what I'm going to present today is part of an NSF-BSF funded project. We have an Israeli team and a US team. And you see here part of the team along one of our field areas along the Arava escarpments in the southeast Negev desert. We have another suite of field areas in West Virginia in the Appalachians. I'm going to talk today only about the insights that emerge from our studies in the Negev. But interestingly, many of our insights also apply with some important variations in terms of the details of the processes and rates in West Virginia. I want to introduce the field team. So first of all, the important people, the students who actually do the work. At the center, you see Elchanan Ariel. He just graduated his PhD in Ben-Gurion University. He's currently doing his postdoc at the Geological Survey of Israel. That is when he's not in Miluim. And then there's Omri Porat, graduated his master, and he's now just started his PhD with Efrat Morin, again, when he's not in Miluim. He's also working on a manuscript based on his thesis when he's not in Miluim. There's Tian Yu Ke, she's a PhD student at the University of Pittsburgh. And then there's the Sean Gallen and Philip Prince. They are mostly working on the US side of the project. And there's Eitan Shelf from the University of Pittsburgh. Some of you may know him. He studied here, and I think that he gave a seminar here about 2 years ago. And there's On Krovi, who sits here. Hi. And myself. Okay. I want to start by introducing some basic ideas about the main landforms I will be discussing today. And the first one is escarpments and cliffs. I'm going to use interchangeably the words escarpment and cliffs, although people mostly use escarpments to refer to tectonic features along passive and rifted margins. And they use cliff in some cases for erosional features. And also cliffs are commonly referred to smaller scale, but in terms of the processes I'll be interested in, they behave similarly. So I'm going to switch in between them. So escarpments and cliff are inherently unstable landforms out of equilibrium. This is because their face is very steep and there is a break in the slope along their edge. So very high convexity. So both high steepness and high convexity in general favor very efficient surface processes that we should expect that eventually bring the landscape closer to equilibrium form and maybe eventually eradicate them. Therefore, it is quite surprising that many great escarpments and cliffs preserve their shape over long geologic time, 10 and hundreds of millions of years, as in this example, you see here escarpment in Oman. They are Oligocene in age, still very linear, about 50 kilometers across. Commonly, when people discuss escarpment, then following the work of Ari, they are divided into two types, and we can apply that also to cliffs. We have arc-type escarpment and shoulder-type escarpment. On your left, you see arc-type escarpments, and they are characterized by a situation where the divide is positioned inland with respect to the cliff edge. And on the right-hand side, you see shoulder-type escarpments, where the divide and the cliff edge coincide. And this basic fundamental difference between them means that they have a completely different trajectory in terms of their morphological evolution. So arc-type escarpment, because you have highland rivers that flow along the highland and down the escarpments in waterfall, they have the power to erode the escarpments and eventually lower them and eradicate them. But shoulder-type escarpments, because the rivers along the highland always flow away from the escarpment, they don't have the power to do that. They retreat backward by cliff retreat processes, maybe undercutting and block toppling. And when doing that, they decapitate, they behead the highland rivers. But it turns out that this dichotomy between arc-type and shoulder-type is too strict. Here are two examples. On the left-hand side, you see an example from the Rheingraben in Germany. and on the right-hand side, an example from Brazil. And what you see here is very sinuous and embayed escarpments and cliffs. These are mostly shoulder type, but locally there are places where there are rivers, such as here, that flow along the highland toward the escarpments. And in these particular locations, the escarpments are pushed backward. They retreat more than the remaining of the cliff, and they invade the cliff. And if you look at this river here, or this one here, you might see that they have a very weird shape. They appear barbed. They appear as if they should have flown in the other direction, toward the highland. And this is going to be a crucial hint for us later on. These are not anecdotal observations. So Tianyu compiled a list of great escarpments that show these particular features. And they are, you can see them here, and it turns out that many of the most famous great escarpments along passive and rifted margins show these characteristics. And there are so many more cliffs like that on a smaller scale. One of them is the Oville Cliff south of Wadi Paran, which I will discuss at length later on. Okay, the next feature I would like to introduce is drainage divide, and specifically dynamic drainage divide and migrating drainage divide. Generally speaking, that's what I like. I like migrating drainage divides. I think we should be very interested in them because migrating drainage divides change the shape and size of drainage basins. That means that they change the distribution of water, sediment, topography, erosion rate, ecological niches across the landscape, and the things that they affect on. For example, isostatic response, orographic precipitation pattern, and everything we care about when we think about long-term landscape evolution. Okay, so since Gilbert's time, more than 100 years ago, we have a basic understanding of why divides migrate. And the reason they migrate is because they have erosion rate gradients across them, and then the divide is expected to migrate toward the catchment with the lower erosion rate. You can see that also here in this schematic diagram. Here the rivers are color-coded by a parameter that we call chi. I'm not going to explain how we derive it. It's based on the topology of the network, and it's kind of a prediction for the steady-state elevation of the river. But if there are chi gradients across the divide, then we should expect the divide, under some assumptions, to migrate toward the catchment with the higher chi value. Okay, currently the state of the art to quantify divide migration rate is to use measurements of concentration of cosmogenic isotopes from both sides of the divide that will tell us about gradients in erosion rate across the divide, and from that we can calculate the divide migration rate. This is what people are doing. But there are several issues with that. It gives us only long-term averages over even 100,000 or even million years. But first of all, the fact that there are erosion rate gradients across the divide doesn't necessarily mean that the divide is actively migrating now. It could also mean that just the slope gradient across the divide is increasing, and maybe the migration itself is delayed. Also, it gives us only long-term averages. It doesn't tell us anything about migration dynamics and rates. We don't know if it occurs slowly and continuously or by jumps, and then we cannot relate it to any of the forcing that acts on the landscape. So one of the topics I'm going to discuss today is going beyond the state of the art. In the setting that we are working, we think we can do much better, and we think we can actually resolve changes in the rate of divide migration for the first time. I have another comment about that. Chatting about divides with the Israeli landscape evolution community, sometimes an issue comes up as to how come divides are migrating if inherently they have no drainage area and therefore no power to do any geomorphic work. I don't see that as a problem. The answer is that divides are migrating in the same way the divides are lowering. Okay? If you have two rivers that bound a divide and they incise rapidly, then they don't leave the divide up high for infinitely amount of time. Even if the divide is on hard bedrock, eventually it will disintegrate, and then blocks will fall to both sides and the divide will lower. The same process occurs for divide migration. It's just that the erosion rate is asymmetric and the slopes are asymmetric, so the blocks preferentially fall toward the catchment with the higher erosion rate and pushes the divide away toward the catchment with the lower erosion rate. Of course, this process is more efficient when the divide is located over soft rock, sediment, soil, but it will happen also on bedrock. It's just a matter of time scale. Okay, after this rather long and maybe messy introduction, I want to start my talk. I'm going to talk about 3 topics. So we're going to see this roadmap 3 times. 2 more times. And the first topic is going to be about a new mechanism we propose for drainage reversal, which is a process which is part of drainage reorganization, which we think is very important for escarpment evolution. Okay, you're looking here at the map of the southeast Negev desert along the Arava escarpment. We are close to Neotz Madal, which is located here. And the rivers are color-coded by the chi value I previously told you about. And as you can see, there are gradients in this chi value across the divide. The divide here is in white. And that means that this divide, separating between the Negev desert and the Arava, is unstable. It would like to migrate further to the west. Another thing that we see is that along the south, the divide and the cliff edge fully coincide. But as we move northward, we see locations where the divide kind of is pushed inward and it loops around some catchments. Let's zoom in on them, and specifically we are going to look at the highlands of Wadi Grofit. Okay, the view is not great, but this is Wadi Grofit, and just by its appearance, it looks as if it's flowing westward. I hope you can see that because it's a bit blurry. But let me add the location of the divide. It's here. So actually it's flowing in the other direction. It's flowing eastward and drains the escarpment in a waterfall. Here is another image showing that. And because of its appearance, we suspected that this is a reverse drainage. It used to flow westward, but it's reversed its drainage toward the east. What does it mean? What is reverse drainage? So drainage reversal is a subcategory of drainage reorganization. It means that a river that used to grade in one direction just reverses its drainage direction by 190 degrees, and now it flows in the other direction, and possibly, as in this case, to a completely different base level. For example, the Red River at the top there is a reverse drainage. Importantly, reverse drainages exploit their antecedent valleys. Okay, so we have the antecedent valley topology. In our field area, there are 3 observations that tell us that a drainage is reversed. First of all, these are bob tributaries. These tributaries that join the main trunk at an angle larger than 90 degrees, as you see the green tributaries up there. These tributaries think that the river to which they join flow in the other direction. And then we have valley-confined divide, a divide that sits within the valley, and a valley is shared in between 2 channels flowing in opposite directions. And finally, in some cases, we have preservation of terraces to the side of the reverse channel that grade opposite to the flow direction of the channel, which is very weird. Let's see these observations in real life. So again, Wadi Grofit, 2 different views, but you can see at least 5 of these barbed tributaries with junction angle larger than 90 degrees. And the camera symbol at your right shows you the location and orientation of the picture from the next slide. So this is the same location. You see here 2 channels diverging from a point, sharing the same valley. Okay? The one at the bottom flows to the east to the escarpment. This is Wadi Grofit. The other one that flows westward is Wadi Aya. So in between them, we must have a water divide. But you have to admit that that's not how we expect water divides to look like, right? Water divides are usually up high along the ridges. And here we have a water divide that sits within a valley. So we call it a wind gap. So it's basically a channel turned into a divide, and it was positioned here because of the reversal. It used to be further to the east, but the section that reversed placed it in this location within the valley. Okay, finally, the terraces. So you see here, again, 2 blurry images of 2 sites of reversal. These are drone-derived orthophotos. The blue lines mark the trajectory of the channel that flows toward the east. The white line is the divide, the wind gap, and the green polygons are terraces that were identified in the field and mapped based on flatness criterion. And let's look at the cross-section. In both cases, we see that while the channel grades toward the east, the terraces that are just to its side grade toward the west. So our interpretation is that these terraces are they preserve the antecedent valley bed before the time of the reversal. And therefore, they grade in the other direction, and therefore reversal. Okay, there is an issue with drainage reversal as to how it occurs. Because if you think about just cliff retreat backward, then this generates a lower erosional surface, and it does not preserve the topology and the geometry of the antecedent drainage network along the highland. So it simply cannot generate barb tributaries. Okay? So more commonly, tectonic tilt toward the new flow direction is invoked. But in many cases, there are no independent evidence for tectonic tilt, but we still should consider whether this is what's happening in our field area. The map that you see here is a map of interpolated surface along the highland. It tries to quantify the grading of the highland of the escarpment based on flat interflows that Elchanan identified. And as you can see, the grading is toward the north-northwest. So the regional tilt is definitely not to the east in this location. Also, if there would have been some tilt toward the east, it wouldn't have been sufficient to tilt the valleys toward the east, because we see that the grading of the terraces still preserve the westward orientation. So the valley bed did not grade toward the east because of tilting, because even nowadays, the antecedent valley bed still grades toward the west. And finally, as far as this tectonic tilting mechanism should be thought of as a general mechanism, if we think about great escarpments, then erosion, the isostatic response to erosional unloading and the flexural response to the deep-rooted normal faults that bound them should actually tilt the escarpment in the other way, in a way preserving the antecedent flow direction away from the escarpment. Okay, so tectonic tilting might not be the answer for our case, so we would like to propose a different mechanism for reversal. The different mechanism is tectonic and structural independent. It only relies on erodibility differences, the ability to erode the material between the valley and the interflows. We assume that the valley is filled with erodible material. It could be valley fill that comes from the antecedent much greater catchment that it has. It could be colluvial fill from the local hill slopes, as we see in this diagram. Or it could even be a softer bedrock to which the antecedent valley has incised. According to this mechanism, the wind gap that we see here, or not seen here, is going to migrate only within the valley, but it's going to stick to the edge of the escarpment along the interflows, simply because of erodibility differences. Stage one is the initial conditions. When an escarpment forms, or when escarpments retreat, it decapitates the highland channel, if we are thinking about shoulder-type escarpments. And as decapitate highland channels, it exposes along the cliff saddles that are filled with sediments. And that's our initial conditions here. So that's the original position of our wind gap. Now, because of the extreme slope asymmetry across the wind gap, then fill material within the valley will preferentially fall down the steep escarpment than in the other direction. And that will push the wind gap inland, away from the escarpment edge, but only locally within the valley. As the wind gap is pushed inward, if sufficient drainage area accumulates, then fluvial incision can start just within the valley. Fluvial incision maintains the erosion rate gradient across the divide, allowing it to keep on migrating backward. When the divide traverses a tributary junction, then suddenly the tributary joins the reverse channel and becomes a barb tributary. But also this barb tributary that you see, a small one here, also it adds its discharge to the reverse channel. So now the reverse channel incised even faster, maintaining the erosion rate gradient across the divide, and it can keep on going. Okay, so this mechanism is tectonic independent. It relies on erodibility differences between the valley and the interflows, and it sees reversal as a process of ongoing divide migration within the channel. Also note the terraces that are formed here. They will be the topic of the next part of my seminar. But before that, let's see if this mechanism is imaginary, or maybe it's applicable to our field area. So to test that, we extracted 2 predictions from the model and looked for their manifestation in the field area. And the first prediction is what is necessary for the initial conditions of the process, and what is necessary is extreme slope gradient along an initial wind gap and a very erodible valley material. So extreme slope gradient is the definition of what's going on in shoulder-type escarpments. Okay? So it's everywhere. And in the valleys, wherever we found reversal, we always saw that the valleys are filled with alluvial-colluvial material. Its thickness varies between 1 meter to several tens of meters. And we can see example of that here. And the interflows are, of course, hard limestone from the graphite formation. I forgot to explain that before. The second prediction is that the thicker the fill, the further the wind gap can migrate. Because the thicker the fill, it can migrate further in order to achieve equal slope, which means more equal erosion rates. And indeed, we see a nice correlation between the length of the reversal and the thickness of the fill. Okay, to summarize this part, we've seen that drainage reversal toward escarpments and cliffs is a common process. We've seen this in the Arava, but in fact it happens in all the locations that were marked on the map and in many others. And tectonic tilt cannot generally be invoked to explain it, and we propose a different mechanism, which is structure independent, and it relies on difference in erodibility between the valley and the interflow. I just want to make one more comment. The tectonic issue is significant because it's very common to find in paper that people infer tilting from observations of reversal. And that's not always the case. So that can change tectonic and geodynamics interpretations. Okay, the second part is currently in review in PNAS. And in this part, we look at several of these reversed setups, and we specifically target the divide, and using very unique record, reconstruct the divide location through time, which allows us to quantify divide migration rate and possibly relate it to one of the forcings that act on the landscape. Okay, so we are going to look at the same diagram, but now please focus on the green terraces. Okay? So note that as the wind gap migrates and the reverse channel incides into the antecedent valley bed, it reshapes the antecedent valley bed, creates these terraces. Now, as the wind gap keeps on migrating, it creates new terraces closer to the wind gap, and the older terraces become older. The wind gap itself is also a terrace from the hydrological perspective. It sees no flow, okay, so it starts aging. According to this model, that means that if we could date these terraces, then their age should increase going from the wind gap toward the waterfall. And the age of each of these terraces should correspond to the time before the present when the divide has migrated toward or slightly past this location. Okay? So that's our target. And we identified one setup, one reversal setup in our field area where such terraces are beautifully preserved. And we call it Malay Tor North. It's to the north of Malay Tor. It's located here. It's a rather small reversal of about half a kilometer. And we have here terraces that are built from the fluvio-colluvial material of the antecedent valley fill, and they grade again opposite to the current active flow direction of the river. We also sampled 2 other wind gaps in 2 other sites. One of them here is the Graphite Aya wind gap, which we previously seen a picture of it, and the other one we call it Aya South. So El-Hanan Deg pits in each of those, and I should explain actually what are these pits. So whenever we are working in a hyper-arid environment, and whenever a colluvial or fluvial surface is abandoned, it sees no more flow, it starts accumulating reg soil. Wreck soil is a type of aridisol that develops by accumulating the aeolian transported particles that penetrate into the pebbles, float them upward, generate this beautiful desert pavement, and also by precipitating different kinds of soils. So Hanan, in each of the terraces, he dug pits, and he described the pits in terms of grain size, chemistry, the different horizons. This was done in On's lab, and then based on well-defined chronostratigraphy, mostly by Kiki Amit, he was able to offer relative dating of these terraces. He also did luminescence, absolute dating of the terraces in Nomi Porat lab. He used OSL on quartz grains, and whenever we suspected that the signal is saturated, he used post-IR IR at 250 degrees on K feldspar grains. So that will allow us, and in each pit he had several ages, one of them targeting specifically the location where the reg touches the original colluvial material over which it develops, which is supposed to tell us about the timing of terrace abandonment or formation. Here are the results of the relative dating. These are for the terraces in Malatro North, and this is the wind gap, and that's going toward the east. And all of these different properties show us aging toward the east. We see here the percentage of coverage of desert pavement, the percentage of fines within the AV horizon, and the maximum concentration of halite and gypsum within the soil. All of them increase toward the east, in a way supporting our mechanism of gradual wind gap migration and gradual formation of the terraces. Here are the two other wind gaps, and in most of the parameters, they show similar values to the wind gap in the Malato site. Okay, here are the absolute ages. I hope you can read them. Overall, what we see is that the terrace age become older as we go from the wind gap eastward. We have a record going backward about 230 kiloyears from this group of 3 terraces, and that means that we can calculate an average migration rate already of about 1 millimeter per year for the past 230 kiloyears. As a side note, based on the same age of the terraces, we can calculate the incision rate with respect to the terrace, and we find that it's smaller by more than an order of magnitude. So in this setting, horizontal changes in the basin shape occur so much faster than vertical incision. So it's a very important process here. We also see that the terraces form groups with similar or even overlapping age. So we have one group here, this is a single terrace, and again, one group here. I want to remind you that according to our model, the age of the terrace corresponds to the time before the present when the wind gap has migrated to or past the terrace. And so clusters of terraces with similar age can only mean very fast migration of the wind gap. And then it stalls, and then it migrates fast again, and then it stalls again. Okay? The present day wind gap, its terrace is about 30 kiloyears old. That means that it was positioned there 30 kiloyears before the present, and it has been there since, stalling. And in the 2 other wind gaps that we dated, we got either the same age or a younger age, which is consistent with the particular setting. By the extent of the terrace group, we could also calculate the instantaneous migration rate of the divide, and we found that during these rapid migrations, the divide has migrated at a rate which is almost 5 times faster than the average. Okay, so we have rapid migration stalling, a very unique dynamics. Let's look at the same terraces again. Here, the x-axis is the age of the terrace, and the y-axis is distance from the divide. And you can see here the groups of the terraces again. And what emerges is a cyclicity of 100 kiloyears, which immediately calls climate, at least to us. Okay? So let's look at reconstruction of glacial interglacial cycles globally, which seems kind of around the same times. And this is Topstein Dead Sea level reconstruction, 100 kilometers to the north of our site. Again, similar cyclicity, but possibly more important, evidence for slightly wetter climate or enhanced geomorphic work from many studies working in the South Negev. Each of these colorful bars represents a different study, different evidence. We can see a cluster of them around 30 kilometers from the present, corresponding to the last episodes of divide migration, of rapid divide migration that we inferred. But there's also some data corresponding to the older episode. Just as an example, these green bars represent spelot and precipitation in caves in the southern Negev from Anton Vax's studies. So I think we see here what appears to be a significant correlation between changing climate and divide intermittent dynamics. And to further explore that, we use numerical simulations. So we designed a 1D, very simple landscape evolution model. It is inspired by the exact topography, or not inspired, it represents the exact topography and topology of this site. It solves the advection diffusion landscape evolution equation. That's the basic equation that most landscape evolution models solve. And it follows the location of the divide through time. And look at the top panel now. What I just exposed are two lines that represent the results of the model for two different simulations. So the dashed gray line here is a simulation where the climate is left constant. This simulation was intended to test the possibility that maybe the specific topology of the catchment induce these episodes of rapid divide migration. Because whenever the divide traverses a tributary junction, then a possibly big tributary with lots of drainage area join the channel, and maybe the divide can be moved faster. But it turns out that with the topology of the specific site, this is definitely not enough. The gray line does not reproduce the pattern of the terraces. The other simulation, the orange one, is one of many simulations where we change the climate. Here the climate changes in between just two states, wet with efficient erosion versus dry with not so efficient erosion, depending on marine isotope stages. And it's so easy to reproduce the pattern of the terraces. So that kind of strengthened our belief that there is some link between changing climate and the dynamics of this water divide. To summarize this part, we've seen direct record of location of paleo divide in different times, through different times in the past. And the migration is intermittent, where transiently the migration rate could be as high as more than 4 times the average migration rate. And we see a relation between the intermittent migration and global and regional climate change. We have lots of thought about the process of relating them, but here I don't have enough time to share them with you. I just want to point out that as far as we know, all of these points were done for the first time. So it's a very special site in terms of the preservation of the terraces that mark the location of the paleo divide. Okay, I forgot to say, if you have any questions, please interrupt me, okay? I still have one full part, so there's time for questions. Okay, yeah?
The chance in the erosion rate coincide with record of more precipitation in the region?
That's a good question. It's a record that is interpreted to be wetter climate or enhanced geomorphic work. I'm hesitant to say more than that because there is a huge debate about what it actually means in terms of precipitation. Maybe, just maybe, same average precipitation, just more stormy. Maybe a different pattern. I don't know. Our data cannot resolve that. But it sees a change. It sees a change. What is this change? It's still not clear. Okay. So far I discussed reversals and divide migration, but I said almost nothing about the escarpments themselves. So this is the last part. Finally, I'm going to get to the point where we look at how initially linear escarpments can become deeply embedded, as we've previously seen. And this is based on Omri's master thesis and manuscript in preparation. Okay, so we should expect the reversal and the divide migration to affect the behavior of the cliff. The reason is that when the divide migrates away from the escarpment edge and we have a reverse channel, then it flows across the escarpment in a waterfall. And if the drainage area of the waterfall is big, that means that the waterfall can retreat faster. Globally, when people look at what controls the retreat rate of waterfalls, the dominant factor is the drainage area, which is a proxy to the water flux and sediment flux, of course, above the waterfall. There are some other factors, but this is the dominant one. So the longer the reversal and the further the divide has migrated, that increases the drainage area at the waterfall that crosses the escarpment, and that allows this waterfall the opportunity to retreat backward and carve into the escarpment and embed them deeply. So we are going to explore whether this situation actually occurs, and for that we are going to a different field site. These are the Ovil cliffs. Here is Wadi Paran. The Ovil cliffs are made of, the lithology is different. They're made of the Meshash chert overlying the Menucha chalk. It's probably erosional cliff and not tectonic. The Tzichor fault is somewhere here. It's further away and not the correct orientation in a way. It's probably formed as part of a strike valley. And maybe Yoav Avni discussed it here once. Okay, let's zoom in into the cliff. And when I'm referring to the cliff, I'm referring to the southern and eastern part of this Ovil plateau. What immediately emerges is that this is a very beautiful cliff. It has very deep embayments. It's very non-linear. The embayments are these features. And in map view, along flow, their length ranges between several hundreds of meters to even 2 kilometers. So these are deep embayments. Okay? I'm going to expose now the drainage network. When we look at the drainage network, so along the highland, most of the channels flow toward the northwest and drains directly toward Wadi Paran. But each of the embayments is associated with a single channel and a single waterfall that drains across the embayment. Well, maybe not surprising, right? Something had to embay the cliff. Okay? Let's also expose the location of the water divide. And as you can see, the water divide in some places is on the cliff edge, but in other, it's further away from the cliff edge. And particularly near the embayment location, the water divide is really further away from the cliff edge. And in between the water divide and the cliff edge, which is the embayed part of the cliff, we see indications that might be already familiar to you. These barb tributaries, okay? And they are everywhere. So let's focus on one of these sites. We see here again 2 channels that share the same valley. And in between them, we have a very low-lying wind gap, a channel turned into a divide, or a divide sitting within a valley. And from the wind gap, we have 2 channels diverging. One that flowing toward you is the one that flows toward the waterfall, and the other one flows directly to Wadi Paran. If we stand on the waterfall, this is what we see. It's about 30-meter high waterfall, and you basically see the embayment. That's the embayment, and here you see the front of the cliff that is not embayed. So, you probably have guessed, right? I mean, what we're looking here is, again, a reversed drainage. And we see the same observations that we saw in the Arava. We see barb tributaries, we see valley-confined wind gap, and in some of the locations we have preserved surfaces that grade opposite, that grade in this direction while the channel is grading in that direction. So, it seems that in this location, there might be some interdependency between the reversal in its associated migrating divide and the cliff and its embayment. But are they interdependent? We think they are, and we would like to propose a feedback mechanism relating one to the other. So here on the left-hand side, you see a cross-section, a schematic cross-section. This is the highland, the wind gap, going toward the waterfall, flowing down the cliff, and here is a map view of the same setup. Importantly, because of the transition between Meshash and Menucha, the waterfalls are migrating along a lithologic contact. So as they migrate upward, as they migrate backward, they don't move upward. They remain at the same horizon. So as the waterfall, if you look at the orange arrow here, as the waterfall retreats backward, because it now has large drainage area, then it becomes closer to the divide. So the slope between the divide and the waterfall increases. That normally means faster erosion rate. That increases the erosion rate gradient across the divide, and as a result, the divide will be pushed away. As the divide is pushed away, then the slope gradient is relaxed, but the drainage area at the waterfall increases. that means that the waterfall can now migrate again. So it migrates again. And the process can continue and be sustained because the waterfall and the divide are coupled. The idea is that if we start from shoulder-type escarpments, this mechanism can explain sustained embayment because the migration of the divide and the reversal increases the drainage area at the waterfall, so it kind of pulls the waterfall with it, but as the waterfall is pulled, it decreases the distance between the waterfall and the divide, increases the slope, increases the erosional gradients, pushes the divide further away. So the process can keep on continuing. The divide really cannot find a stable configuration without just keep on migrating. So is this process operating in our field site? Omri collected several evidence in support of that. I want to share only some of them with you. What you've seen here, there's supposed to be stars here. These are locations where measurements were done. These are measurements of the instability of the wind gap. He looked at slope asymmetry and chi asymmetry. Again, chi is a proxy for the steady state topography, steady state elevation. Chi asymmetry tells us that the divide should migrate. And we see across all the sites that they are unstable, they are asymmetric, and to achieve greater stability, they should all migrate in the direction of the highland. But more than that, it turns out that the degree of asymmetry on the x-axis is correlated with the drainage area. Why would it correlate with the drainage area of the waterfall? Well, it's actually easy to explain that within the framework of this feedback. Because, for example, if the wind gap has just migrated recently, then that means that the drainage area has increased, but the slope asymmetry has decreased. But if the waterfall has just migrated, then that means that the drainage area is smaller, but the slope difference is greater. I want to share with you another correlation, another surprising correlation. Here we look at the slope of the antecedent side, so the other side of the wind gap, versus the drainage area at the waterfall. And we see a very nice correlation between them, which is super strange, right? We are measuring two different geomorphic properties, slope, drainage area, on different sides of the divide. How do they know about each other? Okay? How do they communicate? They communicate through divide migration, basically. If the antecedent slope is very low, that means that the divide should migrate further away in order to achieve stability. Okay? So increasing the drainage area at the slope. Okay, I think we've seen many evidence in support of this mechanism. Let's do another reality check. Here is a landscape evolution model based on LandLab. Again, the same advection diffusion equation that you've seen previously. The initial setup is a shoulder-type cliff with an antecedent drainage network on the top. And the only unique thing in this simulation is that we assume that the channels that you see here are filled with more erodible material. The erodible material goes to a depth of 30 meters, and its erodibility is greater by a factor of 50, I believe. And there's nothing else that goes on. Let's see. So we have here shoulder-type escarpment, very steep cliff, very linear cliff. And that's what's happening through time. Is it happening?
How much rain per year?
I have no idea. It doesn't matter. No, it doesn't. So the rain scale with this time. If you precipitate less, everything that you see here will happen exactly the same. You'll just have to add a 0 here. Okay? It really doesn't matter for these kind of simulations. And let's run it again because it's so beautiful. Okay. So what you see here is that a linear cliff becomes deeply embayed. And these embayments really follow the trajectory of the antecedent drainage network. And the reason for that is the divide waterfall feedback. Because along the antecedent drainage, this is where the divide is migrating, increasing the drainage area of the cliff. So that's where embayment occurs. And as the embayment follow and chase after the divide is pushed further backward. And we see that the embayments are really along the trajectory of the antecedent drainage network.
So how much time was available for the cliffs near Ovid plateau?
For the cliff near Ovid? Okay. I want to answer this question, but after I summarize the talk, because I have a hidden slide about that. Okay? Okay. To summarize, we are close almost at the end, so just instead of summarizing this part, I want to point out that this feedback mechanism has the potential to very simply detach buttes and mesas from receding cliffs. If the embayment just propagates along the antecedent channel, and then it basically could merge and it can detach buttes and mesas. And in our community, how to detach buttes and mesas from receding cliff is a big issue. So here it occurs quite naturally, and we see, for example, here a butte in the Oville Cliff, and here almost a butte that should become, and we do hope to explore this process in more details if we get the funding. So to summarize everything, there are so many take-home messages. I kind of try to extract the most important point of each part. We've seen that drainage reversal toward escarpments is a very common process, and it could occur independent of tectonic or structural tilting. We saw that reversal settings hold an unparalleled record of divide migration in a way that allows us to quantify the divide dynamics and kinematic and its changes through time. And we saw that the feedback between migrating divide and retreating waterfall could explain all of these images of mostly shoulder-type escarpments that are deeply embayed. That's it, thank you. And I can go immediately and answer the question here.
Yeah, so let's answer Danny's question and then finish, and if everybody has another question, you can go and ask their spares.
Okay. So, here is a smart analysis by Omri. The colorful polygons here are abundant fens that were marked by Yoav Avni as Arava Formation. Arava Formation is conglomerate that dates to the Paleo-Paran when it used to flow in another direction. It's mostly colluvial, but also, it's mostly fluvial, but here it's colluvial surface. And these are they are detached from the cliff. They are fossilized, these fans. And Omri used these surfaces and reconstructed the surface toward the cliff. And the lines that you see here is the location where the fans meet the cliff. And our interpretation is that this is the location of the embayment at the time of the deposition of this fan. Now, we don't really have an analytical age of the Arava Formation. It's probably about 2 million years. So that means that at least in this location, the waterfall migrated this distance in the past about 2 million years. So the rates are a fraction of a millimeter per year. That's what we can say.
Okay. So let's thank Liran again.